Hello, everyone. Good day from all over the world. Today we are going to be looking at the topic we already started on the Cayman Physics tutorial channel, and we are going to be looking at another aspect of dimension analysis today. So recently we started the dimension analysis, and I've been able to introduce you guys to what dimension analysis is, and I've been able to put you to what we use dimension analysis for in physics. And I recapping, if I would reiterate, we use dimension analysis for a few operations in physics, like we use dimension analysis to find the units of all of the quantities. If some quantities are dimensionless, right? So, but if they have a unit, it is easier for you to find the unit of that particular quantity with dimension. First find the dimension, then you find the unit, which I showed you guys yesterday, right? So the other part which I'm going to be focusing on today is how to use dimensional analysis to find if a particular formula is dimensionally correct, which means that if a particular formula is dimensionally consistent, the same thing, or if the formula is dimensionally variable, right? We just want to ascertain that this formula is dimensionally correct and is dimensionally consistent. It's good to go with, right? So that is what we are going to be working on today. Right? So that is what we are going to be doing today. So today I have two questions I'm going to be solving with you guys. A lot of questions are on this particular aspect of dimensional analysis, but then I'm going to start with to solve in this video. I'm going to solve just two questions for you guys, and you guys see how we check if a formula is dimensionally correct. If we want to check if this formula I'm working with, is this formula correct? Is this formula going to give me the right results? Is this formula viable to work with, right? So if you go, you see here, down here, I have two questions already that which we are going to be approaching today. The first question is having a formula that you already have aware of, and then the second one as well is a formula that everyone knows. These are just equations of motion that we use in the Newton's equations of motion, right? But these equations have been supposed to be proved viable, right? We just want to recheck. We want to recheck if these formulas that was proposed many years ago, and we have been using it in our equation solutions, and we have been getting our answers for solving questions on mechanics, on dynamics and all of those. So, but we just want to be sure that this formula we are working with, it is correct. It is something that has already been proved viable, right? So it's very simple. Just follow me on as I do this, and you will see how to check if a formula is dimensionally correct or consistent, right? So I'm going to be starting with the first one. Let me move it to a new page, right? I'm going to be starting with that one, and that is what we are going to be working with first. If you look at this, you see this is a formula that is derived from the one of the equations of motion, and they have actually given us the u, which is they have told us what it means, which we all know as the initial velocity. The v is the final velocity, a is the acceleration, and then t is the time at which the change occurs, right? So for that, if you want to look at that, like I said, you need to be able to know what each of the variable is. So we can just write that one out as v is equals to u plus at, right? This is the formula we are working with, right? This is the formula we are working with. V is equals to u plus at, right? So Why we want to work with this formula, we can state what each of the variable means so that we don't get to we get to understand what we are working with, right? We can state what each of the variable stands for. To reiterate, they say v is the final velocity, right? So they say u is the initial velocity, right? And they say that we have the a. They say we take the a as the acceleration, and then we are taking the t as the time at which the change occurs, right? So that is what each of the quantity means. The only quantity here that we still needs to be broken down is very, very simple. We all know is going to be the acceleration. That is the only thing that will still be broken down further. So let's rewrite the equation out, and then we can solve it now and see what it looks like. V is equals to u plus 80. But first we need to talk about what each of these quantity is going to give us, right? What is the dimension of each of these quantity? For the velocity, whether you have the final velocity or you have the initial velocity, is going to give you the same thing, right? Velocity is always velocity. So you are going to have it as a vector quantity. Since you have it as a vector quantity, it's going to be displacement over time, and that is what the formula is. That formula is going to be displacement, right? Displacement all over time. That is what the formula is going to be. So in short, we can as well write it as v is equals to s over t, right? V is equals to s over t, right? This is what the formula is going to look like. So continuing from here, we can as well break this down to find what the dimension is going to look like. So the dimension of that v is very simple. Just what is the dimension for the displacement? That is length. What is the dimension for the time? That is capital T, right? So we can say that the dimension for that can be written as v is equals to, you can put the L all over the T. So at the end of the day, you are going to have the V giving us LT minus 1, right? That is what you are going to have at the end of the day. You are going to have this for the dimension of the final velocity, right? So we have been able to find this. So, and I said the velocity, whether final or initial, is going to be of the same thing. The final and initial just means that this is what we are starting with and this is what we are ending with, right? So whether u or v, we are still going to have the same thing. So we can just say that similarly, the u is also going to give us the same thing, which is LT raised to power minus 1 as well. That is what the u is going to give us as well, right? So go back, we have been able to find what the dimension for the u is. Then we can go to what the dimension for the a is now, right? So as for the a, you can break down the formula as well to know what is the formula for the a and how can I find the dimension. The a is the acceleration. I've written that at the top. If you look at it, and the formula is the velocity all over time, right? If you remember, this is what the formula is. This is what the formula is for acceleration, right? So very simple. We can also go ahead to look for and don't forget, we already have the dimension for the velocity. You can put any of this you can slot any of these into the velocity. You can actually slot whether you are slotting the u or you are slotting v into velocity, and you are going to be getting your result, right? So for the dimension of that acceleration, right, is going to be as a giving us lt minus 1 all divided by the time, which is still going to be give us t as well for the acceleration underneath it, right? So good. The next thing will be to move this t up, which is to make it because this here now is like we are saying we are multiplying the whole of the numerator multiplied by 1 over t, which is going to give us a t inverse, like t raised to power minus 1. So at the end of the day, we are going to have the acceleration to give us lt minus 1. Then you are going to multiply it. When this t goes up, the one at the denominator goes up, it becomes t minus 1, right? So now you can join these things together. You have t minus 1, t minus 1. Finally, your dimension can give us lt t minus 2, right? So that can give us the dimension for the acceleration. Going back, we have been able to get the dimension for the acceleration as well, right? So the next thing now to do is to find the acceleration for the time, which is very simple. We have been talking about that. We have talked about time here. Time here gives us this t. So the time is just going to be for the time, which is the t is just going to give us the capital T, which is the dimension, right? So you can just pull all of these things together, coming back to what the formula says, which says that if you recall, the formula says that we have V is equals to U plus AT, right? So the only thing you have to do now is to insert all of the dimensions first. Don't forget, what we are looking for here is we want to check, is this formula correct? Is this formula consistent? And is this formula viable? Is this a formula that we can be using? Has it been proved viable? Yes, right? It has been proved viable, but we want to recheck, right? So whatever formula that you don't have, you don't know if it's something you can work with, you can actually use this method to find. So continuing from here, you have to just substitute all of the dimensions that you have gotten so far, just put it inside all of this. If you remember, you will recall that we have the V to give us LT minus 1, right, is equals to, you remember that this also give us LT minus 1, right? And then you add the plus again. A is going to give us LT minus 2, right? Then you are going to multiply it again times t, which is what we are going to have there, right? So the left hand side doesn't really have any issue. You can see what we have at the left hand side is just LT minus 1. But on the right hand side, we need to move these things together, right? We can join it together by saying LT minus 1, this is fine, plus. So the other part, which is LT minus 2, we can bring the t inside of it as well, right? You can make it like this. What I've just done here is I've just add this together, right? I multiplied this together. If you multiply that together, you are going to have something like this, right? You are going to have that. That's what you're going to have, right? So with that as well, you can just decide to add this together, to multiply it together. You multiply it together. By the time you multiply it together, because you are seeing the multiplication sign, by the time you multiply that together, minus 2, then what we have here is 1. So minus 2, then plus 1, you multiply it. It's the indices is going to join together. So you are going to probably have something like this. Say LT minus 1, right, is equals to LT minus 1 again, plus, so you are going to have L. So the indices here is going to be 1, so which will give us just one single T. So you can say that minus 2, the multiplication here is going to become addition as a law of indices, then you put 1, right? That's the simplest way to have that done. And we know minus 2 plus 1 is going to give us a negative 1. So you are going to have, you can repeat the same thing downward by saying that LT minus 1 is now going to give us LT minus 1 again, right? Then plus LT minus 1 as well. So what do you notice here? You notice that this now becomes this, right? So if you look at this, you realize that what we have here is LT minus 1, LT minus 1, LT minus 1, but we still have a more compound dimension on the right hand side. This is the left hand side, and this is the right hand side, right? So we can still reduce this to the right hand side a little bit. We can still decide to add this together. Adding that together, the same thing you have here, the same thing you have here is just going to give us 2 times 2 of those, right? So you are going to have LT minus 1 is equal to 2 of LT minus 1, right? So that is what we are going to have there, which is, let me write it here for you to see. So the left hand side is going to probably give us LT minus 1, and then the right hand side is going to give us 2 LT minus 1. So the major thing we are interested in here is the dimension. We don't have any issue with with that 2 you are saying. We don't have any issue with the 2. So the 2 you are seeing there is just a quantity. We don't have any issue with the quantity. So far, the LT minus 2 we have here, LT minus 1, I mean, is the same thing as what we have as the left hand side, is the same thing with what we have at the right hand side, neglecting the quantity. Then this formula, so we can say that this formula V is equals to U plus AT, right? We can decide to now conclude that so far the left hand side of that, the dimension on the left hand side is the same thing as the dimension on the right hand side. Then this equation V equals to U plus AT is dimensionally correct, right? Is dimensionally correct. So that is the first one we are going to be treating. So since we have been able to break down the what is the velocity, what is the acceleration, the next question will not even be taking much of our time, because we now have what the dimension, we're now familiar with what the dimension is. So this is we have been able to solve the first question, and then let's now go to the second question. Let's go to the second question now, and then solve the second question as well. So I'm going to be copying that, and then I start solving that on a new page. So since we already know what it is, we just paste it on the fresh page. Yeah. So now here we have it, right? So now it's easier for us to also work this out. If you read the question, they said to check the correctness of physical equation v square equals to u square plus 2ax, where u is the initial velocity, v is the final velocity, and h is the acceleration, and then s is the displacement. So we have been able to, we just have to recall from here, v is equals to u square, right? V square equals to u square plus 2as. That is what we are working with, right? That is what we are working with, right? That is exactly what we want to work with. But if you recall, you remember that we have been able to, if you recall, we have been able to get some of the dimensions of these things, right? The only thing you are not familiar with is the square, which I'm going to solve it out for you and you will see how it looks like, right? So for the first one, you probably have the velocity to be the same thing we have been doing so far, right? Which is LT minus 1, right? So which is the U as well is going to give you the same thing, LT minus 1, right? So that is the same thing you are going to have, but we will come back to the square on those on the equation. Then the 2, you don't have to worry about that because it's just a constant, right? So, and the acceleration, if you also remember, the acceleration of what we got last in the solution we had previously is LT minus 2, right? And then the one we have not been able to look at is the displacement, which we also did in the last work. The displacement is just L. The difference between the displacement and the distance is that the displacement is a particular movement you have had in a specific direction, which makes it a vector quantity. So the distance is not in a specific direction or in a specified direction, right? So that makes it a scalar quantity. So they have the same in terms of dimension. Their dimension is the same. So the S, which is just going to give us L alone, right? So coming back to that equation, if you come back to that equation, which says that V square is equals to U square plus 2AS, right? So forward with that, we can substitute all of this V, U, A, and S into this equation. We can substitute it into this equation, and you have to be mindful of whatever constant you have there, just like the square, all of the operations you have there, the square, the 2, the addition sign, and all of those things. You have to be considerate, and you have to put all of those things into your consideration as well, right? So let's substitute those things. For the V, we know that we are going to have LT minus 1, then U squared is equals to LT minus 1 again. Then we also have to square it. Then let's write the addition. You can do the addition below, which says that the 2, you have to multiply it times what is the acceleration, LT minus 2, right? Then you have to multiply it again times what the dimension for the for what the dimension is for the displacement, right? So for the displacement now, we are going to just have L. So you can see as well, the most compound stuff we have here, the most compound equation we have here is the right hand side. So you still have to make it merge it together, whatever operations you can do to multiply, to do all of those things and see what your equation will be reduced to. So as a matter of fact, we can just put the square on these quantities, like LT minus 1. You can open the bracket, which is going to give us L square T minus 2 by the time you open that. So the same thing on the right hand side, we are going to have L square T minus 2, then plus. So now we can join all of these things together, right? We can join LT minus 2, then we can multiply it with the L. So, and then the 2 will also come with it. So that will give us 2, right? L can be multiplied with the second L, right? Then can be multiplied with T minus 2. You see that? So that is L T minus 2 multiplied by the L we have outside. So which is, of course, going to give us something very meaningful, which is L square T minus 2. I'm just rewriting the left hand side is equals to L square T minus 2 plus 2, right? 2 L squared T minus 2. So I think the left hand side now is almost getting matched together, because now we have the same dimensions on the right hand side, which is separated by an addition. So what you just have to do, of course, you have a 1 year, so that makes it like you can still compress it together, which is probably going to give us L squared T minus 2, or it's going to give us 3L squared T minus 2. So this is what you are going to be handling with, right? This is what you are going to be handling with. So if you check the left hand side as well, just like we did with the right hand side, you realize that on the left hand side, I'm able to have L squared T minus 2. And on the right hand side, if you neglect the constant you have there, which we don't have any business with, you are still going to be having L squared T minus 2, which makes this equation. So we can conclude and say that therefore v squared is equals to u squared plus 2as is dimensionally correct or consistent, whichever one you want to use, right? So those are the two equations I'm going to be solving for you in this video. The next one I'm going to be going to is, I'm also going to be solving a few questions, like 2 questions. I'm going to be looking at, in the next video, I'm going to be looking at how to get the units of some particular constants. You know, we have some constants in physics like permittivity, we have permeability, we have that one in magnetic field. Permittivity is found in the Coulomb's law. Yeah, Coulomb's law. You can get that one. And then to get the units, it's always very hard for students. It's very simple for you to prove. It's very easy for you to find the units, right? You don't have to put all the unit for every constant. The unit for this constant is always very lengthy. So you don't need to cram it. There's a simple way you can do it using dimensional analysis to solve it out. So that's the next one I'm going to be solving. So stay tuned to this channel, and then subscribe to my YouTube channel, which is Cayman Physics Tutorial. I will be releasing videos for you guys. You guys will be able to ask questions and send me your feedback. And if you have any topic you feel like, oh, you want me to take next after this topic, oh, you are welcome. Send it to my DM and I'll see what I can do about it after we are done with dimensional analysis. Thank you guys. See you in the next video.